Hello, and welcome to G Fun Facts Online, the show that unpacks the science behind our incredible and sometimes terrifying world. I am your host, and today we are stepping directly into the heart of nature's most violent storm. We're talking about those rapidly rotating columns of air that can level a town in minutes. We're talking about tornadoes. For centuries, they were the stuff of folklore and nightmares. But today, thanks to incredible scientific dedication and technological leaps, we are finally starting to decode the complex physics behind these atmospheric titans. So buckle up as we explore the ingredients, the processes, and the cutting-edge science behind how a tornado is born. To understand a tornado, you first need to understand that they don't just appear out of a clear blue sky. They are the result of a very specific and volatile atmospheric recipe. Think of it like baking a very dangerous cake. You need three essential ingredients. First up is instability. At its most basic, this happens when you have a layer of warm, moist air near the ground, trapped underneath a layer of cooler, drier air. That warm air is buoyant. It wants to rise, just like a hot air balloon. As it shoots upwards, the moisture inside it condenses, and this process releases a burst of heat. This release of latent heat acts like a turbocharger, fueling the updraft and making the air column even more unstable. This is what builds those towering, anvil-shaped clouds we associate with thunderstorms, the cumulonimbus. So you have your rising air, but that alone just makes a regular thunderstorm. To get a tornado, you need the second and perhaps most crucial ingredient, wind shear. This is simply a change in wind speed or direction as you go higher up in the atmosphere. Imagine the winds near the surface are blowing gently from the southeast, but just a few thousand feet up they're ripping along from the west. This difference creates a horizontal rolling motion in the atmosphere. You can picture this by placing a pencil between your hands and moving your hands in opposite directions. The pencil starts to spin. That's exactly what's happening in the air. It creates an invisible, horizontal tube of spinning air. This is the seed of the tornado's rotation. The third and final ingredient is a lifting mechanism. You have the unstable air and the potential for rotation, but something needs to give that surface air an initial nudge upwards to get the whole process started. This trigger can be something like an approaching cold front, or a boundary between moist and dry air called a dry line. Once this trigger gives the air its initial push, instability takes over, and the storm begins to build with explosive force. Now, when you combine these three ingredients, instability, a lifting mechanism, and especially significant wind shear, you can create something far more dangerous than a regular thunderstorm. You can create a supercell. Supercells are a special breed of storm, characterized by a deep, persistently rotating updraft known as a mesocyclone. Think of a supercell as a tornado's terrifying cradle. While only about 30% of supercells actually produce a tornado, they are responsible for the vast majority of strong and violent tornadoes, the ones that do the most damage. So how does this mesocyclone form? It's a fascinating multi-step process. First, you have that horizontal tube of spinning air we talked about, created by wind shear. Then, the powerful updraft of the developing thunderstorm acts like a giant hand, reaching down and tilting that horizontal tube of air into a vertical position. And just like that, you have a mesocyclone. This is a massive, vertically rotating column of air, often several miles in diameter, churning inside the storm. On a meteorologist's Doppler radar, this rotation can sometimes create a distinctive pattern called a hook echo, where rain and hail wrap around the mesocyclone, forming a hook shape on the radar screen. When forecasters see that hook, they know the storm has the potential to be very, very dangerous. But here's a critical point. Even with a powerful, spinning mesocyclone, a tornado is still not a guarantee. The final step, the transition from this broad rotation high in the cloud to a concentrated vortex on the ground, is the most complex and least understood part of the puzzle. Scientists believe a few things happen in this final violent stage. One key player is the downdraft, currents of sinking air within the storm. A specific downdraft, known as the rear flank downdraft, or RFD, sweeps around the back of the mesocyclone. This surge of sinking air is thought to help tighten and concentrate the rotation, essentially squeezing it and bringing it down towards the ground. As this happens, another principle of physics comes into play: the conservation of angular momentum. This is the exact same reason a figure skater spins faster when they pull their arms in. By making the spinning column of air narrower, the storm causes it to rotate much faster. This intensification is a key step in forming the tornado's vortex. For a long time, the prevailing theory was that tornadoes formed from the top down. We imagined a funnel cloud slowly descending from the storm's base until it touched the ground. However, recent research, using high-resolution computer models and advanced radar, suggests that many tornadoes might actually form from the ground up, or simultaneously, all along the column. It seems that rotation can be intensified near the surface first, and then stretched upwards by the storm's updraft to connect with the rotation in the cloud. Once that rotating column of air officially makes contact with the ground, it's classified as a tornado. The visible funnel we see is actually made of condensed water droplets, along with all the dust, dirt, and debris being sucked into the vortex. In fact, a tornado can be on the ground, causing damage even without a visible funnel, making them especially dangerous at night or when wrapped in heavy rain. Now, while supercells create the headline-grabbing monsters, they aren't the only tornado makers out there. There are other typically weaker types that form through different mechanisms. For example, you have landspouts. These are not associated with a mesocyclone. Instead, they form when a growing thunderstorm's updraft moves over a pre-existing patch of rotating air near the surface, stretching it vertically until it becomes a tornado. They usually look like a narrow, rope-like tube and are much weaker than supercell tornadoes. Then, as the name suggests, you have waterspouts, which are simply tornadoes that form over water. Some, called fair-weather waterspouts, form just like landspouts in humid conditions. Others, called tornadic waterspouts, are the real deal. They are just regular supercell tornadoes that happen to form over or move across a lake or the ocean. So once a tornado has hit, how do we measure its power? You can't just stick a wind gauge in it, it would be instantly destroyed. That's why meteorologists use the Enhanced Fujita Scale, or EF scale. This is crucial. The EF scale does not directly measure wind speed. It rates a tornado based on the damage it leaves behind. After a storm, survey teams from the National Weather Service meticulously analyze the destruction to assign a rating. The scale runs from EF0 to EF5, and EF0, with winds estimated between 65 and 85 miles per hour, causes light damage. Maybe some shingles peeled off a roof or branches broken from trees. And EF1 causes moderate damage, like overturning mobile homes or breaking windows. And EF2 is where things get serious, with winds up to 135 miles per hour. It can tear the roof completely off a well-built house. And EF3 causes severe damage, capable of destroying entire stories of houses. And EF4 is devastating. Winds up to 200 miles per hour can level a well-constructed house and throw cars. And then there's the top of the scale, EF5. Incredible damage. Winds over 200 miles per hour, and EF5 can lift a strong house clean off its foundation and sweep it away, leaving only a bare slab. These violent EF3, 4, and 5 tornadoes are thankfully rare, making up only about 5% of all tornadoes. But they are responsible for the vast majority of fatalities. With such destructive potential, predicting these storms is one of the most critical jobs in meteorology. While pinpointing the exact time and location a tornado will strike is still beyond our grasp, our ability to forecast the conditions that create them and to detect them once they form has improved dramatically, saving countless lives. The cornerstone of modern tornado detection is Doppler radar. It works by sending out pulses of energy and measuring the speed and direction of precipitation within a storm. This allows forecasters to see the rotation of a mesocyclone long before a tornado ever forms. Modern systems even use dual polarization technology, sending out both horizontal and vertical pulses. This gives a better sense of the size and shape of what the radar is seeing, helping to distinguish rain from large hail, and even to spot a debris ball, a clear signature on the radar indicating that a tornado is on the ground and lofting debris into the air. We also have an eye in the sky. Satellites constantly monitor weather patterns, helping to identify the atmospheric triggers for severe weather hours or even days in advance. And on the ground, powerful supercomputers run complex numerical weather prediction models. These models simulate the future state of the atmosphere, forecasting where and when the ingredients for severe weather will come together. And in the final moments, there is no substitute for a trained human observer. A network of volunteer storm spotters provides real-time, on-the-ground reports of funnel clouds and tornadoes, confirming what the radar is seeing and allowing for the most timely warnings possible. You might associate tornadoes with the central United States, and for good reason. The U.S. experiences more tornadoes than any other country, with over 1,000 on average each year. The region known as Tornado Alley in the central and southern plains is a global hotspot. Its unique geography is perfect for creating supercells, as warm, moist air from the Gulf of Mexico collides with cool, dry air from the Rocky Mountains, all under a strong jet stream. But tornadoes are a global phenomenon. They've been recorded on every continent except Antarctica. Canada sees the second most tornadoes annually, and other hotspots include Argentina, Brazil, and Bangladesh. In fact, the United Kingdom has the most tornadoes per square mile of any country, though they are typically very weak. Our understanding of tornado formation has come an incredibly long way from the days of folklore. From the precise atmospheric ingredients, to the birth of the rotating mesocyclone, to the final, violent descent to the ground, we are peeling back the layers of one of nature's greatest mysteries. But questions still remain. Scientists continue to use advanced computer models, deploy sophisticated mobile radars, and even bravely chase these storms to get close-up data. The goal is always to improve forecasts, to increase warning lead times, and to better protect lives from these awesome and destructive storms. The decoding of the storm is an ongoing quest, a true testament to our enduring drive to understand the power of our planet. Thanks for tuning in to G Fun Facts Online. Join us next time for another deep dive into the science that shapes our world.